Hey guys, let's continue. Yesterday we explored Earth's rotation, which we know is Earth spinning on its axis counterclockwise, 15 degrees per hour. And of course, we had all sorts of bits and pieces of evidence for how we know the Earth rotates. We're going to do the same thing today with a second motion that we call revolution. And we know revolution is the Earth moving in its orbit around the sun. And just like rotation, the Earth revolves counterclockwise. So that makes it nice and easy for us to remember. Right? For example, here's the position of winter. Following winter is what we find spring, and then summer and fall. And so that's sort of a predictable seasonal change because of Earth's revolution. So counterclockwise, the rate of revolution is 1 degree per day. The way we get that is through a bit of simple math, in that we know that one complete revolution is 360 degrees. A complete year, we know, is about 365 days. So if you do the math, it works out to be approximately 1 degree of revolution for every day. Okay, how do we know that the Earth revolves? Several lines of evidence, some of which we've talked about before. This first one, of course, we have talked about, right? We know as we look up into the sky, we see constellations or various patterns of stars, but as we progress through the year and as we move from season to season, month to month, those patterns change. And the reason those patterns of stars change is because the Earth is revolving around the sun in its orbit. And as a result, at nighttime on planet Earth, we see different portions of the night sky and therefore see different constellations. So there's evidence number one, changing constellations. In addition to that, well, here again is that diagram we've seen before, that animation of changing patterns of stars. Aside from constellation changes, one other interesting thing that occurs is that the Earth's orbital velocity, in other words, its speed at which it revolves around the sun, changes. Sometimes we pick up speed and move very quickly. Other times we slow down a little bit. And that's a result of the Earth revolving around the sun in an elliptical orbit. Remember, the orbit that the Earth revolves around on is not a perfect circle. Rather, it has a fairly low eccentricity. But what that means is the sun is not at the center of Earth's orbit. It's at one of the focal points. And since it's located at one focal point, that means sometimes we're closer to the sun. In January, what we call the perihelion position, we're a little over 147 million kilometers from the sun. But sometimes we're at the aphelion position, when we are further from the sun, and we're over 152 million kilometers. So since we're at different distances from the sun, it means that there's differences in gravitational pull, because gravity is in part defined by how close you are to an object. And the closer you are, the greater the gravitational pull. So during our perihelion phase, when we're close to the sun, there's a lot of gravity going on, a lot of pull. And since the sun is tugging at the Earth, we're going to be moving faster in our orbit, as we're sort of being like sent through a slingshot, and we're moving quick. Now that speed diminishes or decreases when we get farther from the sun, because there's a lower gravitational pull. So for that reason, during the perihelion phase, we're moving faster, and during our aphelion phase, we're moving slower in our orbit. Our orbital velocity changes. You may want to note that and indicate that on the diagram in your notes. Similarly, not only do the velocities change throughout the year, but the apparent size of the sun changes throughout the year. And notice I say apparent size of the sun because It's not as though the sun is expanding and contracting. It's not getting bigger and then smaller, but it appears to be getting bigger and smaller because sometimes we're close to the sun. You know, it'd be like if I was standing right next to you, I would appear very large because we know I'm big and buff. But if I'm standing far from you, I might appear smaller, right? Well, and that's what happens when the Earth is close to the sun. The sun's diameter looks very big, and when we're far from the sun's diameter appears to be very small. And so here is an illustration of that, in which you can see that during our perihelion phase, the sun appears larger, and during our aphelion phase, the sun appears smaller. Alright, and that's it for today, guys. Those are your lines of evidence for Earth's revolution.